Hello. Now we will have a short discussion on 3 F's, files, formatting, and functions related to Matlab. First, note about files. We have M files, which are just a list of commands. That's what you've been using them for so far. Just like commands in your calculator or the command window, they just put them into the M file and it marches through them in sequential order and prints the output to the command window. In addition, we have another use for M files, which I'll show you today. That is functions. In functions, you have to put the, well, I'll explain that in a minute. I'm jumping ahead a little bit, but M files can be used for functions. And then the other option, for another thing for files, is you can save your data to a text file, for example, some kind of data file, just like we did in C. We had data files. You could do that with Matlab. That might be handy if you had a huge amount of output and you were planning to either save that for later use or you were planning to load it into some other software, like, say, Excel. You could save it to a file and then open it with Excel. Formatting is not much better than what we had in C++. We have options for controlling the amount of spaces between lines. We have the ability to control the amount of digits that show up. Actually, we have all the same kind of commands that the old C-style formatting had, which is the printf command, and sprintf and fprintf. These are functions that we never really used very much because we were doing output with cout and cin for the input. That cout command has certain ways of doing things. Printf is the old-style way, and Matlab actually has that built into it. And then there's built-in functions to Matlab, very many built-in functions by default, and then many more you can get with certain add-on packages that really extend the power of Matlab. It's where Matlab really comes alive, is where you bring in specialized computational packages that fit your area of expertise. And there's these powerful functions that other people have written, and you can just make use of. It's real convenient if you're into that, excuse me, in that kind of scientific work. Then you can write your own functions. These are similar to what we did with writing functions in C or C++. The difference with us is that we're putting, most of the time you put everything into one file. In Matlab, you put it into its own M file. You put each function into its own M file, and one little quirk about it is that the function name for the function you're calling on must also match the file name, which is quite different than C or C++, where the file name and the function name had no connection. Here, if you have a function, for instance, called find velocity, and you're going to send it some stuff and it's going to calculate a velocity, well, that needs to go into an M file called findvelocity.m. And so that's a little quirk that could hang you up if you're not paying attention to that. One other note, just in case you hadn't picked up on this, for M files, go with real simple names, no spaces, no special characters, just letters and numbers, underscore if you want. For whatever reason, sometimes the extra characters mess up Matlab. All right, so let's go through this lecture 3 that's on the Blackboard site. I'll say a few things about each of these ideas. First, the save command. Let's say I have an array called Z, and Z is 3, 5, 9, a row vector, and then I want to imagine that's a much bigger array, a very large array. I could do save, then I type the name of the file I want it to be. Let's say I want it to be z.txt. Then I need to specify what I'm saving. Just because I said z.txt doesn't mean I'm actually talking about the Z array. So I'll specify the array like Z, and what I usually like to do is dash ASCII ASCII, and now that's been saved. If I go to my directory, the current directory shows z.txt, and if I double click on that, it opens up. There's my 359. It's been saved to a text file. It's currently saved in the Matlab's current directory. Up here it says my documents/Matlab. I could then open that file up with another program like Excel, plot it, or do more computation with whatever other computational tool I'm planning to use. If I transpose to Z, let's say, or I'll call it Y equals transpose of Z. Now it's a row vector or column vector instead of a row, 359. And if I save that, save z.text y ASCII2, now my Z vector, or my Z file now has 359 in a column rather than a row. So it'll print it in the regular matrix form, whatever form it's at in Matlab. It'll show up that way as an array in a text file. So if you have columns of data, you could print columns of data. You'd have to be a little careful about that to make it formatted properly, but pretty much anything can be saved to a data file. Now, if it's a small array like this one, like the one I just had, then you could just copy and paste it. Just selecting the 359 here, I could paste that into another piece of software. The only reason you'd ever, I think, save like this is if you had a huge amount of data, or you were suppressing the data, and you just wanted to go straight to file, then the save option is kind of nice. Now, to make your M-file output look a little better, we have a few options. The first is the disp command. You could put that into your M-file. Let me do a new M-file. If I want to print a message to the screen, first I might have a comment like %, Dan's homework, and then I could say disp and a string can go in here, like problem number 1. And let's run that and see what happens. First I need to save the M file. And after I run it, what appears in the command window is problem number 1. And then I could follow up with my computation along with other, I could have other descriptions of what the problem's actually doing, but you can make your M file output to the command window a lot more readable by including some text. And you can also include numbers, which I'll show an example of that in just a minute. Now, if you don't like that it's only showing a few digits, you can show more of the digits with the format command. By default, format is short. Let me do help format. We're going to switch to long. There's short and long. There's the E and G, which control the ways that the scientific notation appears. And then there's also some other options I won't mention, but you could look at those if you like. And then compact and loose we'll take a look at. By default, it's loose. So if I, for instance, right now print pi, and hit enter, it shows it as 3.1416. If I do format long and then type pi, now it shows more digits. Matlab's running with 8-byte floating point numbers, so 8 bytes, that's about 15 good digits that it's running with in its computation. And when you switch to format long, it pretty much shows all of those. If you were to print any farther, it would be garbage unless you did something to Matlab to make it so it could correctly handle more digits, but by default it can go up to 8 bytes. Then if you don't like that anymore, you could say format short to get it back to the standard. There's also format compact, which I like. Now it cuts out the white space, the extra blank lines. If I type pi, previously when I typed pi, there were 3 blank lines in there, one between every line of output. Now all those blank lines are gone, and it takes up a lot less space on the screen. So that's up to you whether you want to do that or not. The default is loose, which means it shows extra lines. There's also listed in here input from the screen. I'll show you an example of that and this formatting example. The formatting example I'll have to put into an M file so you can appreciate what it's doing. This shows that you can have total control over how the output appears on the screen. When I say total control, it's not nice graphical output like you're used to with Windows programs, but it's just as much control as you would have in a C or C or C++ programming environment. So what I'm going to do is put this into my M file that I started a minute ago. The commands I have, well, first a bunch of comments, and then I say x equals 6, but I suppress that output. I say y equal e to the x, that's exp and x in parentheses, so y will be e to the x power, and then I want to print that to the screen. To do that, I have my sprintf command. That sprintf command is an old C command. It says print to a string, and the F means a formatted print. The syntax here is perhaps a little strange looking to you. If you've been programming for a long time, you've probably seen something like this before. These are formatting characters that leave holes, they leave spaces for certain kinds of information. What I've got sitting there in quotes, single quotes, is a %s, and %s means leave space for some string data, some character data. I don't specify a number, so I'm not saying how much space, just however much space is needed will be used in that hole. And then I have %10.3f. The percent is the indicator that I'm about to give a formatting information. The F means floating point. 10.3 means 10 total columns with 3 of those to the right of the decimal. The decimal also takes a column, so that leaves you another 6 for the stuff in front of the decimal. That would include a minus sign if it was a negative number. And so you've specified exactly how many columns are going to be used and how many of those columns are to the right of the decimal. And then you fill in those holes with here a string, y equals, and then a numeric value, e to the x, or I could have just put y here since I'd already saved it on the previous line. And then I suppress that output. That sprintf command ends with a semicolon, so far nothing has appeared on the screen. And then I simply do disps, and I send that to the display command, and it's going to print that string to the screen. And when I look at I just ran it. When I look at the output, all I see is y equal 403.429. So the label y equals and the numeric value, and if I wanted to, any units after that number could appear all on one line. So it's really compact when you do it that way, as opposed to the default. I'm not saying you have to do a lot of this. It's nice if you make your output look attractive and easy to read, but main thing is to get the computation correct at this point. But you got this extra options to make it look a little nicer if you want to take that time. All right, there's also, in addition to that, the option for user input. This is another M file. I'll paste this into an M file. This command simply asks the user for their name, and then it repeats it back to the screen. Let me get rid of this. I have the command x equals input. Please enter your name. And there's two ways. Input normally is default, input normally defaults to be numeric. If you want it to be string, then you have to include this after the comma, an S in single quotes as an extra argument. And that specifies that it's going to save the data as string data rather than numeric data. And I store that data in a variable called x, and then I showed you a concatenate command before, but actually this is an easy way to add two strings. You just put them together in an array. I've got a quote, your name is, and then I've got comma x as the second entry to the array. Those are square brackets, so y is, you could say, a string array. It's got two strings. And then I display y with the dispy, and it just prints one after the other on the screen. So save this file and run. Notice when I ran it, it actually stopped. It's not finishing the M file. It stops right there and waits for me to type something, just like it did in C++. I'll type my full name with a space, and it reads up. And unlike C, unlike the cout command from C++, it reads until it hits the enter key. So because I typed two names with a space between them, that didn't mess it up. It stored the entire name, first and last name in that one variable called x, and then it printed it all to the screen on one line. So that's a nice feature. You might be using it for numeric data rather than string data, in which case you would leave off the s. There's a lot of built-in functions. Here's a list on the lecture regarding some of the common ones, more than what a lot of programming languages might have. I'm guessing your calculator also doesn't have a arc hyperbolic cosecant or arc hyperbolic secant. Not that there's a lot of call for that, but it's built into Matlab. One function I'm partial to is this atan2, which is a nice one. It's just convenient. If you do the arctangent of, let's say, y divided by x, and you say -1, arctangent of -1, then it comes back with negative 0.7854. Let's take that, convert it to degree measure. So multiply by 180 divided by pi, and it comes out to be negative 45 degrees. So the arctangent of -1 is negative 45 degrees. But maybe I didn't mean negative 45 degrees. Maybe I had an x value that was -1 and a y value that was +1, so that it should have been 135 degrees. Well, with arctangent, that's outside the range of arctangent. Arctangent 2 has that built in. If you say atan2 and you say -1, 1, then it's the same answer because it's y, x instead of y divided by x. Take that times 180 over pi. There we go. There's negative 45. And so that's the negative 45. If I say 1, -1, now it's y is 1, x is -1, and arctangent 2 returns 135 degrees. So you could do the same thing with an if statement. If x is negative, add 180 degrees. But it's nice to just have a function that'll do that for you. So that's an example of just one of the many things that are there. And then if you were to download or order some of those add-on packages to Matlab, this list would grow immensely. I teach a course in feedback control theory where we use Matlab a lot, and we need a lot of those feedback control theory functions. They're really handy, and they do all kinds of things that aren't in the basic version of Matlab. Then the last point is probably the trickiest part, and that's the thing of using your own functions. To do your own functions, you have to put it in its own M file. Here I've got an example called volume. I want to create a function called volume, so I'll copy this, and this time I'll start a new M file. And I've got some comments at the top, and then I've got the keyword function, and then I have the output variable. Now normally you would, if you're writing your own function, you'd say either float or int or void in basically what would be this spot. And then you'd have a return command to return into that spot if it wasn't void. With the Matlab function, you actually give the variable name there. So I'm going to put in brackets the word volume, and volume is what's going to get shipped back to the main program. Then I have the function name after an equal sign, and then I have the argument list, HWL. Those are the names only within the function. Now, there's a big difference here. Even though I'm doing this in an M file, there's a big difference between what I'm doing now and what I did with the M files. When I did it with the M files, that was just an extension of the command window. Variables in the M file, variables in the command window, they're all shared. They're all the same variables. Now that I'm writing a function and I've got the keyword function, this variable list, HW and L, and the word volume, those are all keyed to the function, and they're only visible in the function. And the function will not have any direct access to the main function or the command window's variables. So everything has to be in here. In this case, I'm just doing a very simple program to find the volume of a box. You send it 3 numbers. It multiplies the 3 numbers, stores the answer in volume, but because I've got the word volume here in brackets, the volume is going to be sent back. Note that the name of this function is not volume. The name of the function is box. And so I'm going to save this as box.m. In fact, when I type save, it actually is smart enough to know I should call it box.m. That actually came up as the default file name. So now it's saved as box.m in my current directory. I go back to the command window, and I can actually type the word box. Box, open parenthesis, 2, 3, 5, and it multiplies 2 times 3 times 5, says the volume is 30, or answer is 30. So when I typed box 235, it multiplied them all together, just like, we now have access to that new function, that function we wrote. We can even use that in our own other M files. So our regular M files for the homework can call on the M files that we've written that contain functions in them. Now, if I'm curious what's H, and I say H, it says I've never heard of H. But that's because H is not a main function or a command window variable. H is a function variable. It's in the box function, and it's only visible in the box function. I can't print H here. I don't know what H is because it's internal to that function. Now, a little more complicated example is using there's various minimum, maximum type functions, and one of them I'm going to show you here is f0, which is a function to find the 0 of another function numerically. The math problem we're doing is what's called the Kepler equation. I showed it to you earlier. Start a new M file, and I'll paste this in. The Kepler equation is M equals capital E minus little e sine capital E. We know big M, we know little e. We're trying to find capital E, and it can only be done numerically. There's no algebraic approach to this problem. Rearranging that by subtracting M from both sides, we now have a quantity that should be 0. If we knew the right value for capital E, then we'd have 0. Now the inputs to the function have to be just the iterated variable, capital E. What I have in the function is a single formula, result equals capital E minus little e times sine big E minus M. There's the equation that's supposed to be a result of 0, but we don't know the right value right off, so when we send it an E value here, it's going to be the wrong number initially. It doesn't matter as far as the function is concerned. It's just going to calculate a number and send that non-zero number back. Now the thing is, because the function has its own variable list and it's not normally shared with the main function, we need to have global variables. The word global is a little different than it was used in C or C++. These are common variables. They're known to any function or the main command window if they use this command. So by saying global, capital M, global, little e, that's really, it's just like declaring variables at the top of your C or C++ program. Anything in that file can see those variables and interact with those variables, change them, use them. So by giving this command inside the function, I will have access to capital M and little e. And then let me save this. The name of the function is Kepler equation with an underscore in the word. So file, save as. It came up for me, Kepler underscore equation.m. Hit save. And if I try to run it right now, it's not going to work because it doesn't know what M or E is. It'll try to run Kepler underscore equation. I'll say 0.5. 0.5 is the input value. It says answer equal, and it just gives an empty answer. There was an error. It doesn't know what M or E is. Now, if I say M equals 0.3 and eccentricity little e is 0.2, it's still not going to work. I'll run the equation. I still don't get the answer that I want. Let's clear all. Starting from scratch, I'm going to say global ME, and now these variables will be visible to the function. Say M equal 0.3, little e equal 0.2, and now I can give the Kepler equation command. Kepler equation, let's say 0.5. Whoops, I forgot my close parenthesis. There we go. And it comes back with a non-zero answer, 0.1045. 4, 1. But all I've accomplished so far is I've created a function where I can give it numbers. If I say 0.1, I get a different answer. 0.3, I get an answer that's kind of close to 0. If I keep guessing, I could eventually find out what number gives me an answer of 0, and I'm good with that. But instead of doing that, we did this problem previously with Newton's method. I'm not going to use Newton's method. I'm going to use this f0 function from the, well, it's something you could read about. Its job is to find the 0 of a function. It doesn't use Newton's method because Newton's method requires that you program the first derivative of the function. Instead, it uses some kind of a bracketing technique where it finds two x values, one that gives a positive y, one that gives a negative y, and it just splits it in the middle, and it decides which half to take, and then it just keeps chopping it in half until it brackets it down to a very close answer. It's pretty fast. It's not as fast as Newton's method, but it's reliable, and it'll hone in on a 0 of the function. F0 is the name of the command. Use the @ sign and then your function name. This is pretty cool because what I'm doing is sending a function name to a function, and then I need a first guess. And I'm just going to say 0. This is not that it's trying to find 0. This is just a first guess of 0. It works for a moment. And I found 0.3 was a pretty good answer, but it came up with 0.3729. And so I can double check that. Kepler underscore equation 0.3729. Close the parenthesis. And it comes out to be pretty close to 0. There's a little round off error there. 3.64 times 10 to the minus 5 power. So that's really close to 0. If I had displayed more digits, it probably would have done better. Let's try that. Format long, and then I'll run my F0, and it comes up with a whole bunch of digits. I'll copy those numbers and send them to my Kepler equation function to check its work. I pasted all the number in there, 0.372855 and so on. And yeah, there we go. Now we see it work to as much precision as we could possibly hope for, 5.5 times 10 to the minus 17 power. So we found very accurately the 0 of that Kepler equation for those values of m and e. And that concludes this lecture 3. There'll be 2 more lectures on Matlab later. Thank you.